Okay, so I welcome you guys again to today's segment where we particularly shall be looking at electricity, and in particular, we shall be looking at resistance. So in many situations, especially when we are growing, we use a lot verbally with our parents because by then we thought that our ways were the best ways on how to live life. Little did we know that parents had lived before us, understand ways of life better than we do, better than we did, actually even better than we do. So many a times they would tell us not to do certain things, but because of peer pressure, would do things our way, and we end up contradicting one to another. So I've just said that because I'm trying to introduce to you the concept of resistance. So, like I said, you want to go somewhere, mom, dad says, no, you can't go. But you know that deep down in your heart, that's the best that you can do at that moment. But mom knows better. We tend not to because they have told us not to. So, that in itself, the best term that we can use to describe that very moment is resistance. Now, not on that, I would say, that in many situations, not everything that we do, there are a lot of opposers, especially when you're doing what is good. When you're doing what is good, there are a lot of opposers. So, when I was introducing electricity, maybe current, I talked about the flow. The flow to the, I talked about the flow or the rate of flow, of electric charges in the wire. So when we have a circuit, being parallel, being series, let's say this is our battery. Then we have many components that are connected. We have our ammeter here. Then maybe we put the battery here. We get to have our voltmeter here. I'm just trying to show you. When these charges are coming from the battery, flowing through the wire, they too will find a lot of obstacles as they move. They will find a lot of obstacles as they move. Now, these obstacles that they are finding are the electrical appliances, which are also fighting for the same energy carried by the charges. And at the end of the day, the charges that, the energy that these charges are carrying ended up being given to these appliances, then the appliances are converting to other useful forms, which now brings us to what was discussed as potential difference. So we are saying that the word resistance is just talking about the opposition, the counter reaction in the opposite direction, the opposition to the flow of current or to the flow of electric charges. So when current is flowing, when these charges are flowing through the wire, they will find a lot of opposition. The opposition this depends on the ability that these appliances, electrical appliances, have in converting the energy that the charges are carrying to other useful forms. Now, because it is just the opposition, you want to go out, then mom says, no, you can't go, you have to remain home. How can you measure how much opposition mom provided to you going to the party? We can't measure that. Perhaps we can just compare how tough daddy is when it comes to getting permission from him and how tough mom is when it comes to getting permission from her. We can just compare the toughness, but measuring exact figures how much they do, practically impossible. What are we saying? We are saying that the opposition to the flow of current does not have the instrument, therefore it is not measured. But we can calculate by using the right parameters when they are given. So now those components that vary, those components that oppose to the flow of current, we call them resistors. We call them resistors. So resistors are components or electrical appliances in the circuit that oppose to the flow of current. And these resistors are the examples that we have are quite a lot. We have the bulb is a good example of a resistor. We have capacitors, good examples of resistors. We have many other ones the one that I just called by the name resistor. Resistor, just that. And these very resistors actually are in two types, though I have not, maybe I should have not included this. I should have just said maybe resistors are in two types. Let me say that. Resistors are in two types. There are those whose opposition is fixed. I'll give you a good example of a stove. When you are cooking, the amount of energy that the stove uses for a single set, let's say you are trying to adjust the knob to a value, the amount of energy used at a particular time does not change. It is fixed. Look at a bulb. For as long as there's a normal flow of current, how much the light gives, how much light the bulb gives out is fixed. So the bulb is an example of the first type of a resistor, which is called fixed resistor. So the first type is called fixed resistor. Then there are also those whose resistance, the opposition that they provide, is negotiable, can be changed, can be increased, can be reduced. And that one is called a variable, something changing, variable resistor. The example of a fixed resistor that I talked about is a bulb, among others. The ones that are changeable, the ones that we can vary, the good example is called the rheostat. So the rheostat is an example of a resistor who Okay, so there are quite a lot of fixed resistors, there are quite a lot of variable resistors. These are just a few examples that I have given you. Many, many more will be discussed as we go. Therefore, the opposition to the flow of current, which we are calling resistors, how best can we understand it? So look here, there are these charges that want to move. There are these charges that want to move, and the rate of flow, their speed, the rate at which they are moving, that's what we are calling current. The rate at which they are moving, we are calling it current. Then, as they move, we are also talking about how much of energy is given to them. So basically, we can see that there's something that we can say about current and how much of energy supplied to them, which we are calling it voltage. Because if actually these charges are very fast in the way they are moving, we expect the amount of energy which is supplied to them to be less. I gave an example of someone who is in the queue getting food. If you are very slow in moving from one person who's saving to the other, actually you'll get more food. So when the rate of flow current is less, we expect more of energy to be supplied to them. So basically, we can say that the voltage and resistance are actually inverse proportion to each other. Because when the flow of electric charges is very fast, when current is very high, you'll find that the amount of energy that will be supplied to each coulomb of charge will be low. Therefore, the voltage will be low. Okay, so this is what basically we are trying to talk about. So when the rate of flow of these charges, the rate of flow is very fast, you'll find that it becomes difficult for these charges to be opposed. What do I mean? If someone is throwing a stone from the hands, throwing a stone, it is very easy to contain that stone. It is very easy to contain that stone. We can catch it. We can easily intercept it. We can easily oppose it because the speed at which this stone is moving is quite slow. But now, if this stone is moving at a very high speed, high current, you'll find that, like, let's say the bullet is being fired from a gun. That bullet to be very difficult for you and me to oppose it, to be very difficult for you and me to contain it, because the speed is very high. So actually, the opposition as well as the flow also have some form of a relationship. So resistance is the opposition to the flow of electric charges, and the apparatus or the appliances that oppose to the flow of current are the ones we are calling resistors, which are in these two types: fixed resistor and variable resistor. Okay, questions before we move on? Questions? Any questions, guys?
No.
Okay, so now we are saying these three things now that we have looked at. One, resistance. Two, voltage. Three, current are actually connected by one law. And this law is called Ohm's law. But I forgot to make mention that the resistance actually is measured in ohms, whose symbol is written right over here. So Ohm's law gives a relationship that is there among the three parameters: voltage, current, and resistance. Now, Ohm's law, what does it state? So it states that current passing through the wire, but it's not just the wire passing through the good conductor, passing through the conductor is directly proportional to potential difference, and the inversely proportion to resistance. What does it mean? We are saying that when we have this current, how much of current that we have depends on the voltage. How much current that we have actually depends on the voltage, and it depends less on the resistance. So from here, we are saying if we have current here, which is equal to direct proportion to voltage and inversely proportion to resistance. So this is actually the second formula that we use when finding current. The first one was current is equal to charge, the amount of energy supply, no, the first one was current is equal to charge, which is Q, charge over time. This was the first one, the first formula actually. The second formula was potential difference, which is the same as voltage. Potential difference, which is equal to, it was the amount of energy supplied to each coulomb of charge, which was charge, energy over charge. Then the third one is actually this one. Current is equal to voltage over resistance. So we should not forget where we are coming from. This was coming from the definition of current. Current is the rate of flow of charges, so it was charge over time. Then secondly, we defined potential difference and electromotive force, where we had energy over charge. Then the third one is current is equal to voltage over resistance. So from here, we have some few examples. These examples, when we reach at where they are, I will be hiding them so that we solve with our own answers. Then later on, maybe we can compare. So this is the first question that we have. It says, a current of 2 amps flows through a conductor. The conductor has a potential difference, has a voltage of 12 volts. Calculate the resistance of the conductor. So we are going to use our Ohm's law formula. That current is equal to voltage over resistance. And here we are told that the current that was flowing through this conductor was 2, is equal to, there was so much of voltage which was consumed, and then we are finding resistance. So here we're going to cross multiply. 2 times R, we're going to have 2R is equal to 1 times 12, it's 12. Therefore, if we divide by 2 this side, we also divide by 2 this side, definitely we'll find that the resistance is equal to 6 ohms. The resistance is equal to 6 ohms. Any questions? So we can compare and we'll find the
Sir, you've muted your mic.
Thank you so much, Minana. So I was saying, we have a question which is saying find the potential difference of the resistance whose value is that when the current flowing through it was 4.004 amps. So I was saying we'll go back to the Ohm's law formula, which gives us an indication that current flowing through the wire is direct proportion to voltage and inverse proportion to resistance. So here we have to cross multiply, where we multiply 1 and a V gives us a V, and then I times R is IR. And I was saying that this formula, you have to note it, because not very far from now, we're going to use it. So we have the resistance, which is 1.5 times the current, which is actually 4. And when you multiply that, you'll find that you're going to have 6 volts. So in any form in which this question comes, please be reminded that the Ohm's law formula is very useful. And from this Ohm's law formula, there's another derivation that we are going to find down the road. We will still come back to this. Let this be your not national, not national, but let this be your local anthem. Voltage is equal to IR, or I is equal to V over R. It's not national anthem for you. Let it be your local anthem. That you have to remember it, because we're going to apply this in many ways. So definitely, even the third one is just talking about one and the same thing. So now let's move on and look at some of the symbols that are used. In the first presentation that I was making, when I was just introducing electricity, for those who have not had a chance to attend that lesson, please go and listen from it. I was trying to show you the instrument that is used to measure current. Unfortunately, I couldn't find it in the lab because maybe I was in a hurry. The only thing which was there was a galvanometer. So whenever, and I remember saying that on the galvanometer, the symbol that they use is G. The symbol that they use is G. So whenever you find in the circuit there is this G, capital G, just know that that's a galvanometer. The galvanometer is a very important and useful instrument which you see it under magnetism on the electromagnet. Yeah. So I will not say much about it. We're going to look at it under electromagnet. Then the other component is this one was even discussed, the voltmeter. The voltmeter was discussed as an instrument that's used to measure voltage, an instrument that is used to measure potential difference, an instrument that is used to measure electromotive force. Connected in the parallel circuit, if you remember. Then this is the ammeter, which is used to measure current. This is the ammeter. This way they have indicated, or this way they have indicated, both of them, they represent a bulb. They represent a bulb. Here, we're talking about an open switch. They're just saying switch, but this is an open switch. We can see that this wire and this wire are not in contact. It's an open switch. So for it to be closed, this thing was supposed to touch that end. And then the resistor, this is a symbol that we use. And actually, this is a symbol that is used for a variable resistor. For a variable resistor. Then a fixed resistor, which I gave an example of a rheostat. This is, so it's more or less like the same one that we have in as a fixed resistor. The only thing that we do is that we indicate here with the arrow. And I'm going to show you how this thing is used and how does it vary the amount of resistance that it provides. When you have this, when you have a wire coming from the kitchen, coming from the power supply, from the kitchen, because most of the times that's where we keep the meter or the MCBs. So coming from the kitchen, this wire is going to the bedroom, and then you decide that outside there we should put a bulb. You can connect one from there to give us a junction. And then this one is talking about the wires that are crossing. They are not just crossing, but they are connected to each other. They are not just crossing, but they are connected to each other. These wires are just crossing, one this side, one on the other side, but they are not connected. So you should look at the difference. If they are connected, they should have been tied somewhere there, but they're not tied because they are not connected. One longer line and a shorter one that are drawn across the lines like this, they represent a cell whose voltage is 1.5. They represent a cell. And when you have a group of cells actually they are the ones that make up a battery. That's why in most times we don't say things right. That's why maybe Simon Mwewalen, Simon Mwewa is always there to teach us. Now we call him a Facebook teacher. Because look at the things we put in the batteries. The things that we put in the remote controllers. Are they batteries or are they cells? Because each one of those, one carries 1.5 volts. So do we have to call them cells or do we have to call them batteries? Those are cells. Because the voltage capacity that they have is 1.5. Unless the ones that are in phones, the ones that are in cars, the ones that are in motor vehicles and big generators, those have the voltage above 1.5. That's why we can call them batteries. But you know, this is Africa. So These are some of the symbols that we have, yet we also have many. We have one that looks like this, the ones that look like this. So whenever you see it crossed like that, just know that this is a fuse. This is a fuse. So there are many more that we have actually. There are quite a lot. The capacitor, the blah blah blah, all those have got presentation. So that is what we have here. Now we can now just look at questions. These questions now are involving circuits. These questions are involving circuits. These questions are involving circuits. Let me give you 3 important tips. These 3 important tips are here. Tip number 1. Tip number 1 is, how does a resistor oppose, or how can we use a rheostat to change the opposition that it provides? So I will give you one example. What I'll tell you is what really happens in real life. You want to go for a party. That party that you go for, there will be a door bouncer. That door bouncer is trying to oppose to the entry of people who don't have passes. We are going to have 2 door bouncers, door bouncer number 1 and door bouncer number 2. So this door bouncer is very big. Door bouncer number 2 is very small. Which one of the 2 is likely to stress when stopping people from entering? You'll find that the one who is very small is likely to sweat because it's very small. So meaning for him to stop people from entering, he has to provide a lot of force. This is what happens also to resistors. When the resistor is very small, the amount of resistance they provide is quite big. That's the reason as to why, if you have already observed, the cable that brings electricity at our homes, they are quite big because the voltage they carry is huge. And when you cut the charger, the wires that are inside are actually small because the voltage that passes through there is small. So if we use these small wires in our phone chargers to supply electricity, to connect electricity between the pole and our house, those wires will actually melt because the amount of opposition they are trying to provide is quite huge. As a result, a lot of energy will be given to them. The one thing they can do is to melt. So that's the first point I was saying. The larger the size of the wire, the smaller the resistance, which is opposition that they provide. So when the wire is very small, you expect it to stress just for it to provide a considerable amount of resistance, and vice versa. And, and the opposite is the case. That's one thing you need to understand. Point number 2. Because the ammeter, which measures current, is connected in the series, therefore, current at any point in the series is the same. For as long as it's in the series, at any point that you pick, current is the same. The rate of flow of electric charges is the same for as long as those points that you've picked are in the series. But voltage is different. But voltage is different at any point. Number 3 talks about voltage now. Voltage at any point, voltage at any point in the parallel circuit is the same, and the current is different. So these points are very important. You have to remember them all the way until we finalize. For as long as it's in the parallel, voltage at any point, any of the 2 points that you pick which are parallel to each other, voltage will be the same. And if it's current can only be equal in the series at any point. These tips are the ones that we're going to use in many situations. So look at this. We have this illustration that they've given us. They are now trying to introduce us to circuits. So they are saying that current is the same. Oh, they have even indicated here. So for as long as this is a series, the current that will be here and the current that will be here will be the same. But voltage is different. However, the voltage at this point and the voltage at that point, when they are added, they must be equal to the total voltage that is coming from the battery. So meaning when you have that kind of connection that we're talking about, when power is coming from this side, electricity, the moment it reaches the branch here, the voltage that goes here and the voltage that goes there is shared, is splitted, because it's not equal. Unless current is the one that so the voltage is voltage. The voltage that goes here and the voltage that goes here is the same, because these two are likely to be parallel to each other. So the voltage here and the voltage here are the same, but current to be different. It's the rate of flow, because the moment the charges reach here, the moment they are splitted, the speed changes. Current talks about a speed. So the speed here and the speed here may not be equal to the speed that was there. So as we conclude with our discussion, let's look at this example. The example says, we have been given the diagram. We have the first resistor and we have the second resistor. Resistor also, the point maybe which I should have included, number 4. Resistance in the parallel. Resistance in the parallel. The total resistance in the parallel is found, no, first in the series. Let me talk about the series. Resistance in the series. These terms, these things you need to understand them. Resistance in the series. The resistance in the series is found by, so the total resistance, if you're talking about the series, if there are 3 resistors, you have to say resistor 1 plus resistor 2. If there are 3, just like that, resistor 3. We add them. If they are in the series, you just add them. But if they are in the parallel circuit, we do not add like that. So here we are saying that resistance in the parallel, if they are 2 resistors, you say R2, which is resistance total, which is also called effective resistance, is given by R2 times R1, R2 times R1 divided by R2 plus. So the only difference that we have between what is written on the denominator and what's in the numerator is that on top here we must multiply and down here we must add only if they are in the parallel circuit. So these are the 4 points that I should have indicated there together, but I gave you 3, and this is the 4th one. So these questions that we have, example 1. Find, so we have the resistance, 1 ohm and 3 ohms. The total voltage is 12 volts. So what type of connection are these resistors connected? They are in the series. So to find the total resistance, we are not going to struggle. We'll just add them, R1 plus R2, because they are in the series. That's the reason why we're adding them. That's why we're having the resistance, which is 4. But if they were in parallel, we could have gone by this method. But in the series, we just add them. And that's how we arrived at this 4 ohms as a total or effective resistance. Number B. Number B, it is said that find the current that is passing through the battery or passing through the cell. That is a cell. The cell, no, the battery, that's wrong. So how much current was passing through that battery, which has the voltage of 12 volts? We will go to Ohm's law and say current is equal to voltage, remember Ohm's law, over resistance. And our voltage here is already indicated here, it's 12. And what's the resistance? The one that we have just found, which is 4. So you see how these built-up questions are difficult. If you fail question 1, the answer you are finding on question 1 is what we need to solve question 2. And the answer you are finding on question 2 may be used to solve question 3 or C, D, just like that. So it is very important that we pay attention to the details, because these details are the ones that can actually help us to get all the questions correct. And when you divide, you are going to have 3. Current is measured in amps. This is our 3 amps. That is here. Now, because the question now says, calculate the voltage that is passing through one cell. Calculate the voltage that is passing through one cell. So we said that the voltage here and the voltage here is not the same, but current is the same. So current which is here and the current which is here is the same current that is also passing through the battery. The speed here, the speed there, it's just one way, the speed throughout is the same. So the same resistance, the same current which is passing through here, the same current which is there, the same current is also there. And therefore, we would say that we're talking about voltage, potential difference. So we are saying that PD, which is voltage, is equal to current times resistance, coming from the Ohm's law. So they have indicated the resistor. It is this resistor, only this resistor. How much voltage is there? So the current is the same 3, but we are multiplying by the size of the resistor, which is 1, and therefore the answer is 3 volts. 3 volts. So only 3 volts was passing through here. Or we will say that this resistor could only provide the opposition to 3 volts. What about this resistor, which is here? This resistor, which is here, remember what I told you, that let me even change the color, that the voltage, maybe let me remove this. I said that the voltage in this series is not the same. The voltage which is here and the voltage here, when added, they must give us the total. So if the total is 12 and what is here is 3, therefore we expect what is here to be 9. But we can still use the formula, the same formula here. Voltage is equal to current times resistance. Except that this time around the resistance is 3, because that's the size of resistance which is there. And when you multiply, it's going to give you the 9, as the one indicated here. So basically, this is what happens. It is quite simple if and only if you understand when current is equal, where voltage is equal, where things like that, as well as which formula do we use when you're finding resistance in the series, resistance in the parallel, as well as things like that. So do we have questions? Do we have questions? We can just look at the last one. So the last one is here. What do we have? They have told us that we have this circuit where this is the first resistor. The same one, but they have just changed the arrangement so that we can look at the advantages as well as disadvantages of each type of a connection. So what will be our total resistance? I said the total resistance will be found by multiplying the 2 over dividing the 2. So we're going to say R1 times R2. It's the same, or R2 times R1. It doesn't matter. Then divided by R1 plus, or you say R2 plus, it's just the same. So our R1 is 1 plus 3 over, oh, sorry, it's 1 times 3 over 1 plus 3. And on top there, we're going to have 3 over 4, which when computed, it is 0.75 ohms. So what can we see from here? When the resistors are connected in the series, actually the total resistance that they provide is very, 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 very small as compared to the ones that are connected in the series. So we saw that when they were in the series, the answer was actually 4. Now, because they are in the parallel, the total resistance that together are providing is less than 1. So you should know what that means. Number B, we are comparing, remember? B, we are now told to find the total voltage that is passing through this one here and that one there. Are we supposed to calculate? The answer is no, because the voltage that is passing through the 2 parallel points is equal to the voltage that is actually coming from the battery. So here it's the same 12 volts. Even here, it is the same 12 volts, because the voltage that we have here is the same as what goes here, is the same as what goes here. If voltage was different, meaning when one bulb is connected here, one here, they're supposed to light up differently, but they all brighten up equally. So meaning even C, the answer will still be 12 volts, because we're talking about voltage in the parallel. Yet in the series, resistance 1 actually had 3 volts, resistance 2 had 9 volts. So we are seeing the difference. What about current? Current will not be the same, because current at any point in the parallel is different. So we're going to say current is equal to voltage over resistance. So at the first 1 ohm resistor, the voltage that we have here is still 12, divided by the resistance, which is 1, we are going to have the current of 12 amps. 12 amps. Then what about here? 3. 3, we are going to say the same formula, current is equal to voltage over resistance, but except that this time around, the resistance we're going to use is not 1. We are going to have the voltage of 12 and the resistance of 3. What current are we going to have? We're going to have 4 amps. Then, what about the current that is passing through the battery? The current which is passing through here, which is 4, plus the current that is passing through there, which is 12. When we add them, it gives us the total current which was passing through that. So meaning there are 2 methods. The first method is we are going to add these individual currents. So if the total current total must be equal to current 1 plus current 2, which is the current that we have is 12 amps plus 4 amps, and the answer is 16 amps. 16 amps. But is there any other method that we can use? Yes, the method is there. Which one is that? We'll still go by the same formula. Current is equal to voltage over resistance. Current is equal to voltage over resistance. Now we are talking about total current. So we must use total voltage. What is the total voltage? 12 over. What is the total current? That's what we are looking for. But what is the total resistance? The total resistance that we found was this, which is 0.75. What is the answer? The answer must be equal to 16. Let's just try it out. Where's our calculator? Our calculator is here. So we are saying that we have actually have, allow me to maybe minimize this. We have our calculator here, which is saying that 12 divided by 0.75, and our answer is 12 divided by 0.75. The answer is 16, which is just exactly like the one that we have here. So this is what I was saying, that for as long as your computations are right, by no means you should be deceived. By no means we can be deceived. So this is what we have. Our answer was still 16. You see, that's the beauty of such questions, because the answers are exact and you can even be guided by how your answers are going. If your answers are correct, you find that any method that you use, definitely you will meet somewhere and the answer will confirm with the other one. Questions, guys? Questions? Otherwise, that is what I had for you guys. Questions. If there are no questions, then the recorded will be sent and shared. Who is Kasongo? Oh, okay. All right, guys. Thank you so much. I'm sending you a work that you guys should look at and try if you can solve it.